Welcome to today's session, Accelerating Oracle Workloads using Intel DCPMM and Oracle PMEM Filestore on VMware. My name is Sudhir Balasubramanian. I'm a Senior Staff Solution Architect and the Global Oracle Practice Lead for VMware. I'm joined by my colleague, Arvind Jagannath.
Hi everyone, my name is Arvind Jagannath and I'm a Product Line Manager at VMware and I manage the vSphere platform.
Thank you, Arvind. All right, so without much further ado, let's get started. I'm going to go ahead and share my screen. Okay, so I'm going to move on to the next slide. And this is the agenda for today's discussion. So essentially, we'll start by discussing or talking about Intel DC Optane PMEM on a very, very high level. And we'll talk about how VMware vSphere can consume the persistent memory technology. We'll look at a couple of use cases, essentially running Oracle workloads using vSphere persistent memory. Arvind will then take us across the journey into Project Capitola with some key takeaways and hopefully followed by some question and answers. So moving on. Okay, so let's take a look at VMware vSphere persistent memory concepts, right? And let's look at Intel DC Optane PMEM as well and how the VMware platform can consume persistent memory. Okay, so VMware vSphere version 6.5, well, that was GA'd in 2016. A lot of features were announced as part of the platform release. Some of the notable features that included introduction to persistent memory, essentially the NVDIMM N technology. 6.7, which was released in 2018, that included, among other notable features, it honed and improved or made further improvement to consuming persistent memory technology, right? So as all of us are aware of it, right, more and more applications are needing to process data in real time, and that too in memory. So essentially what happens is businesses, they can gather their insights faster. Customers are looking to scale their memory infrastructure. However, the challenge here is the cost is becoming very prohibitive. And in addition, customers, they would have to pre-provision memory to scale it to increasing demands. VMware has been working with Intel for the last 4 to 5 years on Intel Optane PMEM, the platform, the technology, to solve the latency versus the cost trade-off. And VMware's persistent memory-based solution that helps bridge the latency gap, it aims to provide a seamless way to consume memory. So essentially, what is persistent memory? So persistent memory layer that sits between the NAND flash and the DRAM, it provides faster performance related to the NAND flash, but it provides the non-volatility, which is not typically found in traditional memory offerings. That is, it is able to provide best of both the worlds. So it is able to provide the near performance characteristics of DRAM with the persistence of traditional storage. What does it mean to application? Essentially, what it means to application is the applications can access persistent memory just like DRAM over the DDR bus with the load store instruction, which means the data is now byte addressable, right, or byte accessible with latencies measured in nanosecond versus microsecond, right, which means DRAM lack latency and bandwidth. Now, persistent memory can be configured for use in different modes, right? In 3 different modes, essentially. So the first mode is the app direct mode. The second mode is the memory mode. And the third mode is essentially what's called the mix mode, which is a combination of the memory mode and the app direct mode. So with the app direct mode, which is essentially the slide or the illustration onto the right-hand side, the PMEM and the DRAM DIMMs, they act as independent memory resources under direct load and store control of the application. What happens is this allows the persistent memory capacity to be used as byte addressable persistent memory that actually is mapped into the system physical address space and directly accessible by applications using the direct load store mechanism via a persistent memory aware file system. So the app direct mode capacity that can be used as block over app direct, in which case the driver surfaces a traditional block storage interface transparent to applications, so they don't need to be modified. So essentially, you can either consume it as a byte addressable, which means it's app direct mode, or you can consume it as block over app direct. So you're consuming it as a block device. So the SCSI layer, that driver gets surfaces, and you're able to put your virtual disk on top of that block device. So that's the first mode. The second mode is the memory mode, wherein the persistent memory acts as a volatile system memory under the control of the operating system. So any DRAM that's there in that server, any DRAM that's there in the application, that will act as a cache working in conjunction with the PMEM for caching any of those reads. All right, so this is an example of a host which is in an app direct mode. Essentially, this is how our test bed is set up. So we had a VMware vSphere cluster of 3 Supermicro servers. The version of vSphere was the 7.0 U2. And each of the 3 servers were using the Cascade Lake 8260 CPUs, the family of CPUs. Every server had 4 socket, 24 cores per socket. Every server had 1.5 terabytes of DRAM with 3 terabytes of persistent memory in an app direct mode. And that's what the illustration onto the left-hand side shows. Now, if we were to dive deep into the server configuration, we can see that every server, and as I said before, has 4 sockets with 3 terabyte of PMEM in total, right? So essentially each socket has, in this case, 6 128 gigabyte PMEM DIMM modules, right? Which means the persistent memory capacity per socket is 768 gigabyte. And each set of 6 128 gigabyte PMEM, they are combined into forming what's called an interleave set. So in this example, you have 4 sets of interleave sets, right? And that's what the illustration on the right-hand side shows. So there are 4 interleave sets. Right. The namespaces. So what happens is once we have these 4 interleave sets, right? A namespace is created for every interleave set. Since we have 4 interleave sets, we have 4 namespaces. What happens is ESXi reads all of the namespaces. It combines the multiple namespaces into one logical volume by writing the GPT headers, and the file system format is VMFSL. So 4 interleave sets, you have 4 namespaces. ESXi reads the namespaces, combines them into one logical volume by writing the GPT header. And this would be more clearer in the next slide. So essentially what happens is, if one were to log on to the VMware vCenter, which essentially is the web interface where you're able to manage your vSphere platform, right? One will not be able to look, or one will not be able to see the persistent memory data store, right? And the data store essentially is the storage on which you put your virtual machine virtual disk. But if one were to log on directly onto these servers and navigate to the data store, the tab, you are now able to see the PMEM data store, and one can monitor the PMEM data store statistics using, the ESX CLI family or the suite of commands, right, directly on the ESXi server. So essentially, if one has to look at the persistent memory data store, one would have to log on directly onto the ESXi server. The vCenter data store view does not show the PMEM data store at this point of time. Okay, so all along, we were able to see persistent memory. We saw how we configured the ESXi server with the persistent memory. Now, how can the VMware, or how can virtual machines consume this persistent memory, right? So with persistent memory in the app direct mode, the VMware vSphere platform can consume this persistent memory in 2 ways, right? The first way is the storage over app direct, essentially what's known as the vPMEM disk. In which case, what happens is the NVDIMM capacity, the total NVDIMM capacity of the host, that is presented as a local data store. And then one can then place the virtual disk or the VMDK of the virtual machine on this persistent memory data store, which is backed using the PMEM DIMMs, right? And then what happens is the guest operating system, the guest will access a regular SCSI device or a block device on the guest operating system, and there is no guest operating system changes required. So essentially, everything is transparent to the guest operating system. Everything is transparent to the applications here. Now, on the flip side, if we have to access, or if we have to consume persistent memory as byte addressable, right? One can add an NVDIMM device, and the forthcoming slides will show how one can do that. You're able to add an NV device to a virtual machine. And so what happens is that persistent memory chunk is now exposed as vPMEM, or it is a byte addressable persistent memory, right? And the guest operating system, or the newer guest operating system, or the modern guest operating system and applications, they can use that directly as byte addressable, or if you wish to, you can use that as a block device as well. All right. And that essentially is this is how the virtual machines would look like if one were to consume the persistent memory as block storage versus consuming the persistent memory as a virtual NVDIMM. So if you look at the illustration on the left-hand side, That is the example of how VMs can place their new hard disk or the new virtual device on the PMEM data store, right? So that's completely transparent to guest applications, the operating systems. There is no change to the guest OS or apps. On the right-hand side, the illustration on the right-hand side, one can see by adding an NVDIM controller and a virtual NVDIM device, you are now able to expose that chunk of persistent memory from the server onto the virtual machine, and using a DAX addressable file system, right? Now you're able to consume that persistent memory as byte addressable. So you have these two ways of doing it in this case. All right. So having seen the setup or having seen how virtual machines can consume persistent memory, let's see how we are able to set up Oracle workloads to consume these persistent memory. And let's look at some of the metrics that we got in our test. But even before we do that, right, let's look at some of the challenges with native PMEM and how Intel obtained DCPMM in the app direct mode, which is backed by Oracle 21C persistent memory file store on a VMware vSphere platform, how we are able to address that, right? So with the native PMEM, essentially what happens is native PMEM, they natively operate on a byte by byte basis. It's not a block by block basis, which means any of the data persistence is 8 bytes at a time. On the flip side, Oracle databases, they are based on a block construct, which means their blocks, the Oracle database blocks, they range from 2K all the way to 32K. And for example, if you have an Oracle database with an 8K block, if we have to write an 8K block, you essentially would have to write 1024 times 8 byte persistent memory chunk. And assume while we are doing that, if there is any kind of power failure or if there's any kind of abnormal condition, what would happen is that will result in a fractured or a tone block portions of the block, which means you would have the older data and the newer data, right, in the same block. And that actually results in a database corruption. So the solution here is to use Intel obtained DCPMM in an app direct mode backed by the Oracle 21C or even 19C, the 19.12 persistent memory file store on a VMware vSphere platform. So essentially, what is the Oracle persistent memory file store? It's a pointer switching PMEM file system supporting atomic updates of Oracle database blocks. And essentially that provides external interface for mapping and accessing Oracle databases directly in persistent memory. So let's move on and look at some of the use cases here and some of the metrics that we got with our testing. So essentially, this is the test setup of the virtual machine. As I mentioned before, ESX version 7.0 U2. This virtual machine had 24 vCPUs, 256 gig of memory. All of the virtual disk or all of the VMDKs of the virtual machine was on an all-flash array. Operating system was OEL 8.5 UEK. The Oracle version was 21.5 with SGA, which is the Oracle System Global Area, set to 96 gig. The PGA was set to 20 gig. It essentially is a standalone database with multi-tenant option. We used Oracle ASM for storage management with Oracle ASM library for device persistent. We made sure that all of the best practices when you set up an Oracle database or workload on a VMware vSphere platform, that was followed. And the write-up on the right-hand side essentially tells all of these SCSI allocations for the various VMDKs. So I wouldn't be going through all of that. But what I want to call out here is, if you look at the illustration on the left-hand side, one can see that we were able to add a virtual NVDIM device to the virtual machine. Essentially, in this case, or in this example, 100 gigabyte that we used for our redo PMEM testing. And by redo, it means the redo log for the Oracle database. All right. So our first use case is accelerating Oracle redo log files by using the Oracle 21C persistent memory file store backed Intel obtained DCPMM in an app direct mode. All right. So essentially, we created the 100 gigabyte PMEM device by adding that NVDIM 100 gigabyte NVDIM or virtual NVDIM to the virtual machine. What happens is that emanates as a 100 gigabyte persistent memory device as /dev/PMEM PMEM0 in an FSDAX mode in GOS with partitions. Essentially, as created in a raw mode, one would have to then delete the namespace and recreate it in an FSDAX mode. Once that is done, what we did was we created an ext4 file system, right, with the DAX mode. And then we went ahead creating the Oracle 21C persistent memory file store. So the mount point and the subdirectory is shown as in the write-up here, right? And as we can see, the Oracle 21C persistent memory file store, that is that appears as a file system on user space. So it appears as a FUSE file system in the user space, and that basically reads and writes from the DAX mounted file system, which is mounted in the kernel space. Okay, and this is again, it was a virtual machine on ESX platform 7.0 U2, right? And the load generator chosen here was SLOB, and SLOB stands for Silly Little Oracle Benchmark, and that workbench or the workload or the workload generator essentially written by Kevin Clausen, and the version is 2.5. These are the parameters for the SLOB. Essentially, we set the update percentage to 100%. We set the scale to 90 gigs. We made sure that we set the work unit to 3, and we set the redo stress to heavy. And the reason why we did that is because we wanted to make sure that we set minimum work size. So the work unit minimum size was chosen to drive the most amount of IO with a lot of heavy stress on redo, because we wanted to study the performance effect or the performance improvement using persistent memory. And even before we go into some of these metrics, there is a key thing that I would like to call out. Keep in mind, any performance data is the result of the combination of the hardware configuration, the software configuration, the test methodology, the test tool, the workload profile that's used in the testing. So the performance metrics, the performance improvements that we got here with this workload in our lab, that's in no way representative of any real production workload, which means the performance improvements that one would get for real world workload would be much, much, much better than what we got in our lab here. And the second point that we like to call out is by no means was this any kind of a benchmarking exercise. So if we start looking at this graph here, right? And if you look at the write IOPS, the write IOPS actually increased from 61K per second to 75K per second. The execute SQL per second, which essentially is a very important metric for Oracle DBS, because they use that from the Oracle AWR report to find out if the performance has increased or decreased, between two different variations of the workload run. As we can see from here, the execute SQL per second, that increased from 29K to 36K. The number of transactions that increased from 28K to 36K. So essentially, our write IOPS increased, our SQLs per second executions that increased, the transactions per second that increased, which means there is an acceleration in the workload. And that is basically comparing redo on all flash array versus redo on persistent memory. Now, moving on to further metrics here, right? If we look at these, right, essentially when we start looking at the log file switch completion time, right, that wait time, that log file switch completion wait time reduced from 24% to 22%, and the overall DB IO wait time, that reduced from 20% to 12%. Essentially, the Oracle wait events, right, they are conditions where any session or the Oracle database is waiting for something to happen. So by the decrease here, that essentially is an indication of the fact that there is improvement when one puts their workload on a persistent memory, file system or the persistent memory technology. All right. The second use case that we had was essentially accelerating the Oracle flash cache performance. And let me move on to the next slide here. So even before we go into this setup, or even before we go into this use case, right, what essentially the Oracle flash cache is, think of it like a cache for the Oracle SGA or the Oracle main memory. So what happens is whenever you read blocks from the disk, those blocks are fetched into what's known as the buffer cache in the Oracle SGA. And at some point of time, when all writes are done, which means all of the dirty writes are flushed to disk, right, Oracle would have to reread it again if the DRAM is not big enough for it to cache all of the buffers. By us providing any kind of flash cache or a level 2 cache for the Oracle SGA, what happens is the reads are then serviced from the level 2 cache or the flash cache. So Oracle doesn't have to go down to the disk to reread those blocks. So that's the advantage of using the Oracle flash cache. So our use case here was putting Oracle flash cache on persistent memory and seeing how much is the performance improvement, which means, again, putting flash cache on all flash array versus flash cache on persistent memory. And again, we use the persistent memory file store from Oracle 21C, the same mode of creating the persistent memory device, creating the ext4 file system, making sure we have the mount point of the subdirectory, and then we place the Oracle flash cache in the Oracle 21C persistent memory file store. And yeah, and let's look at some of the metrics that we got from a test. Essentially, we're testing, as I said before, flash cache on all flash array versus flash cache on persistent memory, right? When we start looking at these physical read in blocks, right, we can see that the physical reads, and again, before I go into the metrics, I should mention here that the load generator chosen was again slop, which is 2.5. In this case, we set the update percentage to 0, because keep in mind, we are testing flash cache, which means we are testing for reads here. So we set the update percentage to 0. We made sure that the work unit was set for a larger unit, and we essentially set the redo stress to light, because we do not want any kind of redo or any kind of redo activity happening on the database. We are testing the performance of read flash cache, right? So back to the metrics again. So when we start looking at the physical reads per blocks, what we observed, right, was the physical read blocks per second that increased from 45K to 316K, which is phenomenal. The read IOPS that increased from 45K per second again to 316K per second. And the execute SQL per second, which I mentioned before, was or is one of the key metrics, right? The transactions per second, the execute SQL per second, those are key metrics to find out what the, or to find out if the performance of an Oracle workload has increased or decreased. That phenomenally increased from 65K per second to 142K per second. So there is an increase in the physical reads per blocks. There is an increase, a phenomenal increase of read IOPS, and there is a phenomenal increase of execute SQL per second. And all of these metric increases, they point to the fact that the workload performance has increased simply by placing this workload on persistent memory file store, which is backed by Intel DC Optane PMEM on a VMware vSphere platform. All right, more metrics to come. So essentially, again, when we start comparing the flash cache on all flash array versus flash cache on Oracle PMEM Filestore, if we start looking at this overall DB IO wait time, I mean, what was amazing was the overall DB IO wait time that drastically reduced from 38% to 0%. When we start looking at the operating system, at an operating system level, when we start looking at the CPU sys percentage, that reduced from an average of 8.5 to an average of 1%. And if you start looking at the IO weight, that was drastically reduced from 40% average to 0%, which means we were basically able to cut down on the IO weight. Overall, we were able to cut down on the overall DB IO wait time. We were able to almost cut down on the overall percentage system, simply because of the fact that our flash cache is now on persistent memory. So Oracle doesn't have to go down to any kind of storage unit to read any of the buffers that basically slid down the Oracle SDA over to the flash cache. Flash cache being in persistent memory, it's accelerated. So the flash cache performance is accelerated, which means now we are able to run more SQLs per second, more transactions per second. Okay. So at this point of time, I'm going to hand this over to Arvind to talk about Project Capitola.
Thank you, Sudhir. Now let's talk about a brand new initiative at VMware called Project Capitola. This is an innovation we are starting with the Intel Optane persistent memory at VMware. Next. So let's start by looking at some motivation first. So what we are seeing is, as businesses engage in digital transformation, some important trends are emerging. One of the trends is that trends for compute. So there is a higher demand for compute, but then we don't have the equivalent memory to support that compute. Another trend is that data is definitely increasing exponentially. It has grown a lot, especially over the last few years. But with enterprises, traditional DRAM itself is not able to keep up and not able to scale to meet this growing data demand. So DRAM growth is actually slow compared to the CPU cores growth, as you see here. Another trend is that enterprises are trying to reduce costs, and the OpEx model is becoming more common, and they are trying to postpone server investments. And that's why sometimes you see growth in the cloud kind of infrastructure. So even though we see all these trends, server DRAM capacity is slow growing. And server memory sizes to support the applications are still continuing to increase. And servers, we see servers with capacities of, for example, 0.5 to 1 terabyte of memory still increasing, which means that server prices are increasing too, that enterprises are using and are allocating. So, but what we see is at the same time, some of the critical data intensive workloads that are running on these servers need to run in memory, and they still need to perform real-time processing. Now, there is a need for newer memory tiers to support the larger capacity and scale requirements. But we still need the speed and latency characteristics of DRAM. So really, even though we have the extra capacity provided by PMEM, we still need to solve the latency problem. But Project Capitola is a software-based tiering that can combine DRAM with other memory technologies such as Optane. And it can provide a very good TCO reduction, at least 20 to 30% is typical we see with performance close to DRAM and when used with Intel Optane PMEM. Thus, Capitola can definitely help solve the density and capacity problem. It can also help scale the capacity on demand. Next slide, please. So in this slide, you'll see how Capitola aims to provide a single address space. Basically, Capitola will provide a sum total of DRAM and persistent memory capacities. The tiers are all used together and there is no caching as such. Workloads such as VMs and containers, they will be fully agnostic of the underlying memory hierarchy. And ESX kernel will expose one contiguous memory that can be allocated to these workloads. In the first phase that we are working on at VMware, we'll be providing two tiers, tiering between DRAM and Intel Optane persistent memory. So again, this is a fully homegrown software implementation bolted on to the kernel, as opposed to any hardware mechanisms. And thus, it will not require any special SKUs or any separate licenses, and it will just be available as a software feature. The target launch for Capitola is early next year. Next, please. This slide shows sort of the evolution that VMware is looking towards. So the vision is to really take Project Capitola further and support it for a fully disaggregated and pooled memory architecture. So hosts in a cluster will be able to take advantage of a shared memory resources, which means that this can further help reduce TCO for customers by avoiding some of the over-provisioning kind of issues. CXL is also a major part of our plan, and it will be part of the Project Capitola in this architecture. We are also exploring other tiers that can be connected by CXL or by NVMe or Fabric. And we are exploring and trying to make this part of our future vision. Next slide, please. This is a roadmap, quick view of the roadmap for Capitola. Currently, phase 1 is in progress. We delivered phase 0. Phase 0 was all about VMware building a memory management system that keeps track of some of the key memory stats, and it monitors not only DRAM, but also persistent memory. We work with Intel to get some hardware statistics, and we can even provide workload specific monitoring at both VM and host level. So Capitola can actually use these statistics to also provide faster failure recovery, for example, by monitoring memory bandwidth, latency, miss rates closely. And it can basically ensure that all the workloads get a fair share without any such problems as starvation or noisy neighbor or rogue VM kind of issues. DRS algorithms also make use of these statistics, and they can further ensure that the workloads are load balanced across the cluster. So phase one is where we are right now, and we are planning to deliver Capitola next year, as I said. And we are also seeing a lot of server OEM and customer interests already. We'll be adding other tiers like NVMe, and we'll be supporting a mix of the various persistent memory modes that Sudhir talked about in the next phase. And like I mentioned, CXL is high in VMware priority, and we'll be supporting combinations of tiering with CXL. The VMware Vision, again, is to support a disaggregated, pooled, and composable model. Next slide, please. Here, we show a quick overview of the technology. On the left side, we are showing a logical view. So for simplicity, we are just showing a two-tier physical view, which means that there are only two tiers, but there is no reason why this cannot be extended to multiple tiers. And basically, the logical view is what the VM sees, which means that ESX exposes a contiguous memory, and then all the VMs or containers are able to take chunks of that memory. And they are agnostic of whether this comes from PMEM tier or DRAM tier or any other tier. Now, with the physical tier, that represents where the VM's volatile memory is actually physically placed. And vSphere will decide the placement of pages in the appropriate tier based on activeness. And vSphere, the ESX kernel will shuffle between the hot and cold pages based on using certain heuristics. And again, the memory available, it will be the sum of all the tiers. Next slide, please. Next. Let's build it, please. Okay. Okay, so let's look at some performance numbers. So this shows the DRAM performance. So here we are using two tiers, DRAM tier, which is the faster tier, and the PMEM tier, which is slower. So the amount of DRAM given in this experiment is 32 gig to a VM, controlled via some config options. The remainder of the 32 gig comes from persistent memory. So x-axis represents the amount of DRAM and PMEM given to the VM, which is basically the sum total of all values will be 32 gig. The graphs themselves have been normalized to the performance seen by the workload when using only a pure DRAM kind of performance. So the general guidance for PMEM, as we have specified in some of our official documentation, is to not go beyond 1:4 ratios. So there are two tests, software tiering disabled versus software tiering enabled. In the disabled case, PMEM is used as an extension of DRAM, and in the enabled case, ESX is actively moving hot and cold pages between DRAM and persistent memory. So the key takeaway is that even in this case, you will see that there is only an 8% performance degradation, even if we use persistent memory, and we see that the workload that we are utilizing is actually crossing the bounds of DRAM. Next slide, please. Next. So let's look at some of the key takeaways from this session. First, digital transformation is definitely leading to a larger data sets and real-time analytics, and it's requiring more performance. Memory is costly, it's hard to scale and manage, and it's requiring new software-based solutions. Applications are also becoming real-time, and they benefit from being in memory. And mission critical applications like we saw with Sudhir's experiments, with Oracle, they also benefit from such innovations. So VMware's project Capitola is bringing software-defined scalable memory solutions to address customers and applications challenges for today and for the future. Next slide, please. All Oracle on VMware collateral, including the Oracle on persistent memory collateral, can be found in the link below. Next slide, please. It was a pleasure to present this session. Thank you for watching.
Thank you for listening to us.